Hello everyone. In this video we're going to be talking about solution concentration. And so now that we know what solutes are and what solvents are, we now need to discuss their relationships. And so one thing you need to understand and to remember is that solutions are mixtures. And if you recall, mixtures can have varying proportions. And so an example I have here is salt water. And so if you take salt water from the Corpus Christi, and then you take some saltwater samples off the coast of Antarctica, and then say there's some salt water somewhere on Mars, those are all going to be classified as saltwater if they have some salt and water. But taking into consideration the amount of salt, some might have different proportions. Some may have less salt, some might have more salt. And so when we talk about how much solute is in a given volume of solvent, we talk about the concentration. And so dilute solutions have a little amount of the solute in a given amount of solvent, whereas concentrated solutions have a large amount of the solute in that given amount of solvent. And so please note I said both times in a given amount of solvent. So please notice in both of these flasks we have the same volume, but in this concentrated solution we have a lot more atoms in that given volume. Whereas in this dilute solution, same amount of volume, less, again, scientific term here, less stuff. And so in these cases, another example I can hopefully, again, more familiar to you than salt water, is Kool-Aid. Again, if you don't add enough Kool-Aid to your, Kool-Aid sugar to your water, then you're going to get a dilute solution that probably just tastes like really, really watered down strawberries, whatever your favorite kind of Kool-Aid is. Or on the other end, if you add too much sugar, you might end up actually chewing on some of those sugar particles as you're taking a drink of your Kool-Aid. And so in which case you would have a concentrated solution. And so it would be really kind of silly and ridiculous if we walked around the chemistry lab saying, hey, I need that hydrochloric acid that has a lot of HCl in it. And so more specifically, chemists use the term molarity to talk about these concentrations. And so molarity just kind of gives some limitations on what extremes we can have in terms of volumes. And so molarity is always going to be the amount of your solute in moles divided by the volume of your solution in liters. Or more, succinct, it's going to be molarity is equal to moles per liter. And so please note the main important aspects of this combination is the volume of your solution is going to be in 1 liter, always 1 liter. And so the moles will be different, the amount of stuff will be different, but the volume per solution to solution to solution is going to remain the same. And so anytime you see this italicized M that follows a number, then either mentally or even physically scribble out this M and write moles per liter as its new unit. And the great thing about something like moles per liter, you've seen this in the past in the form of grams per milliliters or grams per moles, it is nothing more than another conversion. And so the same way that we can convert from mass to moles and moles to mass using molar mass, we can do the same thing with molarity, but now we have a conversion between moles and liters and moles, or more specifically volume in moles. And so, as I mentioned on the previous slide, if you see an M following a number, mentally or physically scribble this M out and write moles per liter. And so if you have a 0.500 molarity sodium chloride solution, that means you have 0.005 moles of sodium chloride for 1 liter sodium chloride solution. Or you can kind of flip that around and say in 1 liter of our solution, it contains 0.500 moles of sodium chloride. So if you're given the molarity, as long as you keep 0.500 moles with the sodium chloride with the moles and the 1 with the liter, you can flip this all day long depending on what kind of conversion you need to do. For example, if we need to solve for the molarity of an aqueous solution that contains 0.715 moles of glycine and 495 milliliters. And so as I stated earlier, if we want to figure out the molarity, it needs to be in the form of moles per liter. And so given here is 0.715 moles of glycine. If you want to know molarity, you need to put it over the volume. But the only volume we're given here is 495 milliliters. So let's just place that there, let's say a placeholder for now. As I tried to stress a few minutes ago, or a few seconds ago again, then we need to make sure that our volume is in liters. And so using some good old dimensional analysis here, we can convert our milliliters into liters, but please pay attention because milliliters is on the bottom. We do not want to divide by milliliters. We want to, again, make sure that milliliters is on top. And so in this case, milliliters will cancel out milliliters on top there. And our overall final answer, just by following where the units are, is going to be moles per liter. Or if you want to be more specific, moles per liter is going to equal molarity. And so in order to calculate the molarity of any compound, you need to know the moles and you need to know the volume. Sometimes this problem will be given to you, not this specific problem, but a problem will be given to you and we will tell you grams of your substance. But by now, hopefully you're familiar with how to convert grams to moles. Same deal with the volume. As you can see here, we don't always give you the volume in liters, but you need to make sure the volume is in liters before you get your final answer. So one more time. Amount needs to be in moles. Volume needs to be in liters. But once you have the molarity, the scheme you've seen a couple times already, it's just going to keep growing and growing and growing. And so back in chapter 2 or 3, we discussed how to go from moles of a substance to entities or to things or atoms or molecules, doesn't matter, using Avogadro's number. We also know how to go from moles to mass by using the molar mass. So all I'm really doing here is just giving you another conversion to the almighty powerful mole. And so now if you're given volume, we know how to go from volume to moles. And so in this case, and again, this will come up in a later video, but if you have atoms, convert atoms to moles, you can go to mass now or you can go to volume. If you have volume, you can convert into moles, now you can go to mass or you can go to atoms. So here, converting into moles, hopefully by now you understand, very important math. You need to know how to do that. So example of how to do things like that, let's look at this problem right here. So how many grams of a solute are in 1.75 liters of 0.460 molarity sodium hydrogen phosphate? And so in this particular problem, I am now asking about grams, but I give you volume. And so you need to understand how to use molarity as our brand new conversion. And so if we're starting off with liters, I have the volume of the solution. But as I've mentioned a few times on this video, if you have the molarity, you can convert from volume to moles. And so here, just to exemplify this, liters cancels out with liters, you get moles. And then once we have our moles of solute, doing some stuff that we've been doing for a while, we are going to convert moles into grams by using the given molar mass. Here we have moles cancel out moles, and now we're looking at grams. Luckily, that's where we wanted to be. And so, say that we have a really strong pitcher of really nasty tasting Kool-Aid right now, because there's so much sugar in there, it's just you can't drink it anymore. And so in order to fix that, we do something very fancy called dilution. And so in dilutions, one thing you have to understand is only the volume is changing. And so if you have a very concentrated container of Kool-Aid, you're going to add water to it to make sure that it tastes a little bit better. You are not going to add water and more Kool-Aid because that's completely defeating the purpose. And so whenever you dilute a solution, you are adding more water, you are adding more solvent, you are not adding any more of your solute. And so in that situation, your moles will remain exactly the same. In this case, again, same amount of atoms are going to be in concentrated solution that are going to be in your dilute solution. But if you look at the volume again, a lot less, meaning that these atoms are kind of packed much closer to one another. But as soon as you add more liquid, you have a lot more volume for these atoms to kind of start spreading apart. And so, one more time, moles don't change, your volume changes. But because molarity includes both the moles and the volume, that means if you change the volume, you're changing the molarity. And so one thing I have to point out, and it's kind of out of order on this slide here, but this equation, M1V1 equals M2V2, only works because you are not changing the amount of moles. If you don't change the amount of solute, this equation will work perfectly fine. But, and everybody please write this down as you're listening to me talk about it. Even like hit rewind so you hear me say it again. Molarity is the only thing that is saving us here. The moles in both of those solutions are not changing. And so that is the only time you can use M1V1 equals M2V2 is when the moles do not change. And so later on in this chapter, we're going to start talking about titrations. And I promise you, at least half of you are really going to want to use this equation. Don't do it. It's going to be a huge mistake. And so, going back to the beginning, my first bullet point on this slide, most of the time when we as in chemists who actually have a license to do so, when we order chemicals from a chemistry manufacturer, we usually order them in high concentrations. And so even if we wanted to only have a 0.01 molarity hydrochloric acid solution, we can't really call up a chemical place and say, hey, can you send us 0.01 molarity? They would laugh at us because they make one and only one of the higher concentrated stuff, and then they send it to you and say, you do all the work in order to make it as dilute as you want. And so typically these things are going to be called your stock solutions. They are the solutions that have most of the time the highest concentration you can have because you can make any kind of dilution from those. But whenever you go through and make these dilutions, remember, you're only changing the volume. You are not changing the amount of stuff that's already in that solution. And so this equation of M1V1 equals M2V2 only for dilutions. So please, please, please remember that. Do not use this for anything else unless I'm telling you I am adding more solvent to this container. If I say anything about adding any more acid or adding more base or adding any more anything that is not the solvent, this equation becomes null and void. And so one time you can use it, like I said, is for dilutions. And so say that I want to prepare a 3.00 liter of 0.5 molarity calcium chloride from a 10 molarity stock solution. I want to know what the volume of the stock solution is required for this process. And so we can use our M1V1 equals M2V2 because nowhere in this question am I saying that I'm adding more calcium chloride. All I'm saying is I need to figure out how much water to add. And so using M1V1 equals M2V2, I know my M1 is 0.500. I know my V1 is 3.00. I know my M2 is 10.0, and I'm looking for my V2. And so here, again, technically you don't have to split this up into moles per liter, but I just wanted to show you in this example that liters will cancel out those liters, these moles will cancel out those moles, and then your liter down here is going to be the only thing that's left over after all the math. And so whenever you kind of plug this into your calculator, 0.5 times 3 divided by 10, you end up with 0.150 liters. And so, something I have to draw your attention to in this particular problem is I tell you that I want a total. I want 3.00 liters of my 0.500 molarity calcium chloride. Do not read this as me saying that I'm going to add 3 liters of water. Because if I were to add 3 liters of water to my already present 0.150 of my calcium chloride, I am no longer going to have 3 liters. And so the way that most chemists do dilutions is we use some fancy glassware that we call volumetric glassware. So in this volumetric glassware, the picture I have depicted here, this is going to be what they call a 3-liter volumetric glassware. Please notice there is no graduation lines. There is no lines or tick marks that represent 1 liter, 2 liter, 3 liter, or 1.2 or 0.01 or anything like that. And so on this piece of glassware, there's one line and only one line, and that line has been perfectly calibrated to represent 3 liters and exactly 3 liters. And so instead of us having to measure out 0.150 liters of our stock solution and then subtract that from 3 and then measure out 2.85 liters of water somehow, which there is no awesome graduated cylinder that measures out 2.85 perfectly. And so in order to avoid all the other hassle about it, if we use this volumetric glassware, we pour our 0.15 liters into the flask, and then we just fill it up to the line with water. And at this point, we know we have a total of 3 liters. We know this 3 liters of solution was made with our 0.15 liters of our 10 molar. Using this calculation, we hopefully again should have our 0.500 molarity. So one thing I need to remind you of is some questions may be written in such a way that it's going to say that we added this amount of solution to 10 milliliters. But one thing you have to remember is if that is the case, you need to add those two values to each other. And so if I say I added 3 liters of a concentrated solution to 10 liters of water, you need to make sure that you add the 10 and the 3, because your V2 is going to be the sum, or it's going to be the total amount of solution after you have completely finished this dilution. And so you can't forget that if we're talking about adding two solutions, add the solutions. Don't just use the individual values.